Okay, so I'm going to talk about dynamical mean field theory and how do you use this to get important information in solids. So just like Rebecca explained us, how can you, just looking at the structure, get a feeling for the Hamiltonian. What we usually do when we use these numerical methods is that we try to do the calculation and try to get insight into material by looking at the output of the calculation. We look at the total energy, we look at the spectral functions, we look at the two-particle vortex function, get some idea of low energy interactions like Andre was talking about in the morning. For example, what is the renormalized low energy interaction? You need to look at the two-particle vortex functions, for example, isn't it? So these are the type of outputs that you can get with these numerical methods. Some are easier to get, and you will, in the evening, in your tutorial, you will see how to calculate, for example, the spectral functions. Some are harder to get, like two-particle vortex function or effective interactions. These are much more expensive to do, but are doable. It's something that is now a big focus in this area of research, how to calculate effective interactions at low energy from the two-particle vortex function. Okay, but the first lecture is supposed to be very simple, just the basic idea of what is dynamical mean field theory, how this relates to DFT, density functional theory, why is it a good idea to combine the two, and then I will try to convince you that the local correlations are the first that you have to take into account. Just like Rebecca today in the morning explained that first you need to take into account your on-site terms, isn't it, that block the hopping, isn't it? That's the first term. And then you add the hopping to it, okay, through bands, of course, that appear, or kinetic energy, and then solve this in some good approximation, isn't it? That's the basic idea. Now, tomorrow, most likely, I will discuss about a little bit more advanced terms. For example, the exact double counting. This was in this area there was a big problem of double counting of correlations between DFT and DMFT, which was recently solved. Then the important point here is that we need to work with so-called stationary free energy functional, with which we can calculate forces on atoms, and this allows us to calculate crystal structures, equilibrium crystal structures, optimized crystal structures, which is very important because it turns out that your properties change dramatically with the change of the crystal structure. I mean, that's extremely important area. And well, hopefully we're going to discuss a little bit the forces tomorrow. Now, a big picture point of view. So the modern material design tries to solve so-called inverse problem, doesn't it? So given the functionality, what is the best material which has that functionality? That's what we want ultimately, isn't it, in solid state? So typically how we approach this is that we have, we take some constituent atoms from a periodic table, and then we create a big unit cell, and then we figure out whether this, what is the most likely crystal structure. There was a lot of recent developments in this area where people search over all possible crystal structures, doesn't it? And they try to find the best crystal structures, the best candidates for a crystal structure. Then they try to figure out whether the compound is stable by looking at the phonons, looking at the comparison of energy, trying to see whether constituents or smaller, simpler materials have lower or higher energy. So the question is whether your material that you predict has lower energy than similar materials from which it is made. And then finally, if you see that your structure is stable, then the question is what are its properties and whether it fits your original idea of what you want to solve, doesn't it? So that's an important game in town that lot has been recently done by the density functional theory. And as you know, density functional theory works really well in many weakly correlated systems, doesn't it? So therefore, there was actually a huge success recently. And what made this huge success? What's the reason that this success appeared, for example, this decade, isn't it, for materials genome, for example? Well, basic law of physics, or Schrödinger equation, is known from 1920s, isn't it? Dirac famously said that all the laws of physics are now known. The entire quantum chemistry and physics, solid-state physics could be solved if we could have a good approximation how to solve, or good idea how to solve these equations. Now, DFT came somewhat later, and that's an efficient way to solve the Schrödinger equation reasonably well, let's say. And that took some time. Nevertheless, DFT is now, well, already 30, 40 years old. So what was really important is development of efficient implementations and fast computers. So development of methods to predict crystal structures came maybe 20 years ago. Then development of methods to predict useful properties are still evolving. And finally, fast computers. And you put all this together, and all of a sudden, you have like a little revolution in solid state. Okay, so for example, BCS theory and Nash-Bloch theory are known for 60 years. And people didn't predict high-DC superconductors until recently. Okay, so this is actually one of, in my opinion, one of the triumphal stories in predicting high TCs. They are not unconventional. These are conventional superconductors where Nash-Bloch theory can be applied, and therefore people could actually get TCs within few percent. Okay, but this was indeed, in my opinion, the first prediction of new high-temperature superconductor. Okay, so it came just 2 years ago by the group of Haule, and their prediction was that lanthanum H10 has here very high TC of the order of 260, 280 Kelvin under pressure. Okay, that was pure theoretical prediction, and experiment was made by two famous groups this August, August of 2018, and they both find superconductivity very nearby. So close to 250 Kelvin is the latest measurement. So this was really pure prediction. One of the few in condensed matter where such a brave prediction was made and it was measured within the year or so. That's quite remarkable. So DFT then has done a fantastic job for weakly correlated systems. And of course, hydrides are pretty weakly correlated, we could say that. I mean, lanthanum here, you might have some question whether it's, empty. Lanthanum is usually empty, isn't it? It's F0. In this case, maybe not completely empty, but still, it seems it's pretty band-like, so therefore DFT works very well, okay? So at least when you have phonon-mediated superconductivity, then DFT is really a king. Done a lot of great things, okay? However, in correlated systems, it's not that easy. Life is more complicated. So the idea of materials genome was that we would put all existing materials in a database, calculate physical properties from it, and then our computer scientists, our colleagues, could do some searching in the database and find all kinds of interesting phenomena. But of course, in correlated systems, that's not that straightforward. So I selected here a couple of materials with which I worked on, and in which dynamical mean field theory works very well. So it predicts all important properties of it. And I checked for one of the most famous projects in materials genome, materials project. And so, and the question is, how well do they do? Okay. So VO2 in a rutile phase, P42 MMM, is well-known metal. It's close to the metal-resonant transition, so it undergoes metal-resonant transition, but in the rutile phase, it's clearly a metallic. And if you look at this database, they predict a gap of 1 eV. So then you look at the lanthanum 2-copper-04, which is parent compound to high TCs, isn't it? We know it's multi-insulator. Then you look at the database, it doesn't have a gap, so it's metal, according to the database. Then you look at the strontium 2-iridium-04, which we heard about in Rebecca's discussion. So this is multi-insulator as well. You look at the band gap in this database, it doesn't have a band gap. So then you look at the strontium VO3, it's metallic. Well, you look at this database, it has a gap of 0.3 eV. So all of them are wrong. FeO, rock salt, multi-insulator, look at the database, well, it doesn't have a gap. So most likely, if you have a correlated metal, if you have there's D orbitals or F orbitals which cross the Fermi level, then this database most likely will not work. Okay, so and what's the simplest way to understand why this fails? Yes, question? Yes.
The same paper has predictions for rare elements like cerium, praseodymium, pyrites. Those have F elements.
Yes.
And they predict low ATC.
Yes.
How reliable can those predictions?
Well, again, I think that there is some luck involved here, to be honest. Even in lanthanum H10, if you look carefully, there is F at the Fermi level, and the fact that there is a lot of F at the Fermi level helps boost TC, okay? So therefore, in my opinion, even lanthanum H10, they were somewhat lucky to get that, okay? Because generically, if I have time, I will talk about this later. What happens in many systems where you have some correlations is that typically electron-phonon coupling is bigger than what's predicted by DFT, but the density of states might be lower than what's predicted by DFT, and there are some cancellation of errors, which sometimes you get really lucky and get it right. So you're right, whenever you have something like lanthanum or cerium or any of those, then you have to be careful, okay? But if you don't have those, then DFT is actually pretty good. Okay, so what's the reason for, or what's the easiest way to understand from the band picture how the correlations occur? Okay, so the simplest way is the article problem of strong correlations in H2 molecule. Okay, so if you have two hydrogen atoms and you put them close together, okay, then it turns out that many mean field methods do a pretty fantastic job. So Hartree-Fock, LDA, GW, an exact result, okay? So you look at them, look at close to the equilibrium, they all give more or less the same minimum in the same place, okay? The total energy is not so great, okay? But the minimum is more or less where it's supposed to be. So therefore, when it comes to structural predictions, all of them are reasonable, okay? However, when you pull the two hydrogens apart, you're supposed to get just hydrogen atom, isn't it? Two hydrogen atoms. Well, however, how does this occur? Well, because the double occupancy has to go to 0. So the probability that you will have both electrons on the same hydrogen has to go to 0. So this is this double occupancy here, isn't it? Probability that both electrons, two electrons, will occupy the same ion has to go to 0. Well, you know what? If you do any mean field method, you will do some type of decoupling, isn't it? Like n up and down, and you will get a finite number. So double occupancy will never go to 0, and you're in trouble, okay? So, and that's the reason why all these mean field methods here, Hartree-Fock, LDA, and also GW, which is beyond mean field, but nevertheless doesn't take into account correct atomic limit, doesn't take into account the fact that when you pull atoms apart, that the double occupancy has to go to 0, okay? All the methods that don't have that fail in the strong equated limit, okay? So if you want to have a method which will describe correctly the strong equated limit, you need to have the atomic limit exact. Okay? And the DMFT, as far as I know, is the simplest method that has that. The atomic limit and the band limit, okay? Both has to work, okay? So this is the problem here in all other band theories. Now, excited state properties are also challenging within DFT. Well, why? Because DFT is not supposed to work for excited state properties, isn't it? It's a ground state method. So therefore, typically, in almost all solids, especially in correlated metals, you will see a mass normalization. So if the spectral function within LDA is predicted, or bands are predicted to be like this curve here, then the experiment typically has smaller bandwidth, typically, okay? So, well, I want to advertise LDA plus DMFT, which we're going to discuss here a lot, and then you see that this mass enhancement indeed is there in the theory, okay? Why? Well, because when you solve this so-called quantum impurity model, you see that the quasi-particle peak forms, doesn't it, which has mass normalization, and this mass normalization is what makes bands typically narrower, okay? But in addition to narrower bands, you also have some incoherent spectra, which is many times also seen in experiment. For example, this peak here is some incoherent spectra that's left over because quasi-particle peak doesn't have all the weight in the quasi-particle peak. Okay, so now, we should not completely discredit density functional theory. As I said at the beginning, this is an extremely successful theory, okay? What's important, in my opinion, is to understand why does it work so well. In my opinion, that's very important. We many times forget how good a density functional theory is. Right? So And what does it do? It relates some aspects of the solution of the real problem to the solution of more tractable auxiliary problem, which is the electron gas plus system of independent particles. Okay? So basically, you're targeting here not the entire solution of the many-body problem of the wave function, which is extremely hard to calculate in complicated solids. What you're targeting is charge density and total energy. Okay? And this can be done reasonably well. Now, another important point is that even purely local exchange correlation in LDA and GGA, subject to a mean field type self-consistency, gives total energies and charge density surprisingly well, okay? Really well. So what do I mean with that? Well, as you probably know, in density functional theory, you write a functional of total energy, which is a function of charge density, and then you write this in terms of material dependent part, which has to do with the place where the nuclei are, isn't it? This is V external times rho. This V external is just the periodic potential due to nuclei. And then you have kinetic part, which you can write down reasonably well. It's basically nabla square. And then you have the interacting part. The interacting part you split into something which is very, very large, the Hartree term. Hartree term you always need to take into account exactly because it's too big to make any fudging with it, doesn't it? And then the rest is what you call exchange correlation term, okay? And for this exchange correlation term, it turns out that even purely local ansatz is pretty decent. And that's how 90% of calculations are done. I mean, GGA has another correction to it, but the first approximation, LDA is doing almost as good job, okay? And this is LDA. So we need to understand what this ansatz is, okay? So this ansatz means the following. You take charge density at any point in space, R, okay? And you just map this point in space, each point in space, independently to a problem of electron gas, okay? So each point in space is independent from any other point in space for this step in which you calculate exchange correlation energy density, isn't it? So this is exchange correlation energy density that depends only on the density at one particular point and no other point, okay? And then you just integrate this over the space, okay? So therefore, this is as local as it can get. It's a local to a point in 3D space, okay? So that's what DFT is. So to summarize this with a picture, so this you can think of a complicated solid. So what you do is in order to determine this exchange correlation part, of course, you solve the Hartree part exactly. You solve the nabla square kinetic energy part exactly. But in order to solve the rest, the exchange correlation part, so what you do is you map each point in space to a problem of uniform electrogas, okay? And then this gives you an effective potential, which we sometimes call V quantum, and then this defines you a non-interacting problem of a solid, an effective mean field non-interacting problem of a solid, which you can solve. And the important point is the Dyson equation is solved for all electrons in the problem, okay? It's actually very important. Many times we want to get some basic understanding of the system, and therefore we produce a low energy model. Here, the philosophy is very different. Don't try to produce low energy model. Solve the Dyson equation for all the electrons in the problem, okay? Don't just be happy with the lowest one. Because why is that reasoning? You want to have something that is working in almost every solid. Well, not in correlated solids. But if you don't have strong correlations, then this would always work, okay? If you try to construct a low energy model, each system will have a different low energy model. Some will have simple one, some will have complicated one, doesn't it? So you don't know. But here, this philosophy should work everywhere. At least philosophy should work. Now, yeah.
Other than the total energy and the ground state density, charge density, what are the other things that can be measured in this method?
Well, that's a good question. I mean, we always look at the bands, isn't it? Now, literally speaking, you shouldn't look at the bands because, yes. But on the other hand, it turns out that they're usually pretty good. Fermi surfaces, for example, is another thing which actually should be correct. Fermi surfaces themselves, isn't it? The mass enhancement is a different story. That should be wrong. But usually in weakly correlated solids are pretty decent.
So when you showed the spectrum in this LDA plus DMFT, that's not of any auxiliary system. That is really the calculation of the
Yes.
spectrum.
Yes. I mean, I will try to argue later on that within the Luttinger-Ward approach, you can actually get exactly identical equation the DFT delivers, exactly the same philosophy, exactly the same set of equations and the same codes you can use, but then it's an approximation for the spectra. It's an approximation for the bands, okay? So in principle, within this Luttinger-Ward approach, you can say, well, let's look at the bands. They're just one possible approximation for your bands, which is the most local one, okay? So, yeah. Now, in correlated solids, as I discussed, electrons have dual nature. They're partly attenuated and partly localized, and cannot be described in the simple terms with auxiliary non-interacting system. So we need an auxiliary system which does take into account some interactions, local ones in particular. So therefore, we need to make sure that at least this double occupancy can go to 0 when you pull apart electrons or ions, okay? So reducing this double occupancy then leads to narrowing of the bands in metals and ultimately to mode physics. And where DMFT is really stellar, much better than most of other methods, is at predicting this mode transition, okay? At least in frustrated systems. So metal and insulator, they can describe at the same time. It can now, by having forces, we can also calculate the structure at the mode transition or through the mode transition. That's something that we can do now and we couldn't do in the past. So in more general case, we have orbital physics, Hund's interaction, and so on, and they all play an important role. One can get orbital differentiation, orbital selective state, Hund's metals. It gets complicated. As Rebecca showed here, there are complicated terms, Hund's interaction, there are crystal field splittings, you have spin overcoupling, all these terms, isn't it? And all these terms are taken into account here, okay? All the local terms are taken into account exactly, okay? And non-local terms are taken into account within mean field, okay? So that's the general philosophy. Now, and therefore, what happens is from rigid band picture, where you have bands, which means for each momentum k, you have a well-defined sharp peaks with weight 1. These are called bands, isn't it? You go into something that has quasi-particles with some fractional weight, and the distribution of spectral weight over a large energy window, okay? So in order to describe this correlated solids, of course, we couldn't just talk about bands. We have to go into the spectral description, isn't it? You have to have this description in terms of spectra. Now, how do we achieve that? Well, I will discuss this later on, how we get to DMFT to be the simplest or the first order approximation in this direction. The idea is the following. In DFT, what we do is we map each point in space to a uniform electron gas. That's the right auxiliary system. Why? Because, well, uniform electron gas is the simplest interacting system. Okay, so that's why you choose it, isn't it? If you could have something else, then you might use something else. But that's the simplest interacting system for a single point. But when you don't have a single point, you have a single ion, let's say, then the auxiliary system turns out to be quantum impurity model. Why? Because in quantum impurity model, you have one full interacting site with all the on-site terms that can be taken into account exactly, and then an infinite bath of conduction electrons, doesn't it? So that's the correct auxiliary system. So what we do is we map this problem of an ion in a solid. It has to be in a solid, doesn't that? This complicated ion in a solid with all the crystal fields and so on. We map this to a problem of quantum impurity. It's a complicated quantum impurity, but that's something we can solve now. And then you solve this only for the purpose of calculating so-called self-energy, which is a dynamic equivalent of effective potential, constant potential. So in DFT, you calculate constant potential. Here you calculate something that becomes now frequency dependent, energy dependent. Why? Because we need energy dependent spectra. I mean, energy dependent, well, distribution spectral weight. So therefore, this delivers so-called self-energy on the given ion. Now, of course, we can also relax this and we say instead of ion, we will take into account a cluster, okay? And that can be done in some instances, okay? In terms of theory, it's completely straightforward. The problem is, of course, that the quantum impurity then becomes very complicated and it has a sign problem typically. And sign problem is hard to, within Monte Carlo, sign problem is a hard problem, doesn't it? So therefore, the cluster calculations are a little bit less frequent, okay? But the single site problems are completely straightforward to do. Now, the important point here is we want to solve Dyson equation for all electrons in the problem. So we don't want to construct a low energy model, at least initially, okay? We want to solve Dyson equation for all electrons in the model, just like what we do in DFT. You don't want to do DFT for a Hubbard model, doesn't it? That's usually not a good idea, okay? So we want DFT for everything. In the same philosophy in DMFT, you want to do for all electrons, doesn't it? Then, of course, if you're interested in what your solution means, you might produce a low energy model, and then, of course, the life becomes simpler, isn't it? And then you can understand more physics. That's, of course, very valid question. Okay, now, in order to understand how this mappings works and why do we get this impurity, I want to step back a little bit and give a historic overview of how DMFT was born. Okay, so the idea comes from classical statistical physics, which you probably were taught in your school, namely, for if you have a spin system and you're in high dimensions, actually high dimension just means that you have large connectivity Z, okay? Then in the limit of large connectivity Z, you can map a lattice problem into a problem of single spin in a Weiss field, in an effective field, doesn't it? So effective field where the magnetic field is determined by, well, all other spins around that site. Now in the same way, you can do it quantum mechanically. So this is classically, this is quantum mechanically. So when you do quantum mechanically this for the fermion, what happens is that you end up in a problem where you have one interacting site in a mean field, okay, in a mean field bath. This mean field bath has to be fermionic. And it turns out that this is exactly quantum impurity model, okay? So you can also write this effective action, how you go from a lattice to a site, but that's really straightforward. So the point is, in infinite dimensions, this is exact mapping. So in large dimensions, this is exact mapping. One can use usual power counting rules to see that this is exact. Now, of course, the usual question is this any good in 3 dimensions, okay? And at first sight, it's not obvious at all, okay? Now, experience, of course, shows us that, well, it's very good, just like DFT is very good, isn't it? So, but the worst case scenario is 0-dimensional case. It's a molecule 0-dimensional, isn't it? It has it has one site and one neighbor, okay? So that's how we want to look at the H2 molecule. One site plus one neighbor, okay? 0-dimensional thing, H2 molecule. I mean, if I use this as a cluster where I correlate both sides, then of course this is trivial, okay? This will always work. But if you take into account just one site plus one neighbor, that should be disaster within DMFT, doesn't it? Okay? Well, it's not so bad. So here is the result of, I'm showing again the Hartree-Fock here, then I'm showing LDA, GW, and finally DMFT, an exact result, okay? So what do you see? Well, it's better than LDA, it's better than Hartree-Fock, it's better than GW, it's the best, okay? Especially LDA plus DMFT is really good. Hartree-Fock plus DMFT, well, the question is, what do you add to DMFT? Because you have to take into account in some way Hartree term and maybe exchange term, isn't it? The question is whether you take into account exchange term exactly or you don't. So you do it Hartree-Fock plus DMFT or LDA plus DMFT. So the point is that LDA plus DMFT seems to be fantastic. It's the best. And if you zoom this in, you see Hartree-Fock plus DMFT, LDA plus DMFT, an exact result. So total energy in this case has an error of 0.2%. Okay, fantastic. And in particular, what you see is that at large separation, this is exact. Why? Well, because we have exact atomic limit. So this is something we could guess, isn't it? Exact atomic limit. Impurity has exact atomic limit. There are problems around here where the molecule breaks. Why? Because at the point where the molecule breaks, you do need to take into account non-local correlations. Okay, so that's a place where, of course, corrections are needed. So the cluster corrections are essential. Yes. Yeah, it has to be large basis set. This has 30 orbitals, yeah, roughly 30 Gaussians. No, exact result is exact result. I mean, this is, you also take a lot of orbitals to get the exact result, and you do exact denization. So there are lots of methods to do H2 exact. But even in LDA plus DMFT, we had to take into account many orbitals. This is 30 Gaussians. So this is not a single single orbital problem. But we correlated only single orbital. That's very important. So the correlations here are put only on a single orbital. So in other words, what you're solving is a single orbital impurity problem, okay? But you keep lots of other states which are treated in mean field. That's how this is solved. And you get a fantastic result, okay? So you correlate just one orbital and lots of other orbitals which are treated in mean field. So depending how you treat Hartree-Fock plus DMFT of LDA plus DMFT. Yes, yes, yes. Yes, exactly. So it's only one impurity with one orbital, which you can do it on a laptop very quickly, okay? And all the rest are in mean field. It cannot be so bad because you know that even Hartree-Fock is decent and LDA is decent, so you have to be better. But what is interesting is that it's so much better. Okay. Okay. So this dynamical mean field theory was introduced in the context of lattice model, so it's usually is the easiest to understand it in this case. So this was done by Gabriel Kotlin and Juan George, and so how do you write this down, or how do you take this into account on a computer? Okay. So well, you have to relate the local quantities with your impurity quantities. Okay. Which local quantities? Well, the Green's function, the self-energy, and the on-site interactions. Okay, everything they have local. This has to be set equal to impurity, and then impurity gives you information that you need. Okay, so in particular, the simplest way to look at it is you have to calculate your local Green's function, and then you equate this to the impurity Green's function. The impurity Green's function, in you solving the impurity, gives you self-energy on the impurity, and then you use this as your local self-energy, and that gives you then your local Green's function. That's one way to look at it, isn't it? So if you have a simple Hubbard model, then you can write this down within such an equation. So this thing here is so-called impurity self-energy, isn't it? It has an improper self-energy, which we call hybridization function. Then you have the real self-energy, sigma ii, isn't it? This is the impurity Green's function. And this is the lattice Green's function with local self-energy, isn't it? And in sum over k, you get the local component of it, okay? That's for the simple Hubbard model. Of course, you have to generalize this in general to a complicated system at hand. Now, this was kind of, let's say, hand-waving derivation of DMFT. There's a better way of deriving the same thing, and this is functional point of view. And it actually gives you something in addition to just DMFT equations. It tells you when can you derive your approximations from functional, which can be made stationary. Stationary means that the first order correction, when you make an error of the discretization of a computer, will vanish. Okay, that's very useful when you have a numerical method. Now, when you do this functional point of view, the basic variable here is not the charge density like in DFT, but it's the Green's function, isn't it? So the Green's function is the basic variable. And then you write down a functional which gives you the free energy, okay? Free energy. And this functional is actually, well, one of those functions, there are many, but one of those which I like to look at it is so-called Luttinger-Ward functional that has this form, okay? So it has universal functional, like a DFT, and then it's a material-specific one where there is hidden the nuclear potential, isn't it? Now, one has to be a little bit careful when discussing this Luttinger-Ward functional. Maybe you heard latest discussion about the issues with this Luttinger-Ward functional. So if you brute forcefully numerically try to optimize Luttinger-Ward functional, you will see it has multiple solutions because it's highly nonlinear, isn't it? So in addition to the solution that you're looking for, you will probably find many other solutions, okay, which might be unphysical. Some of them are unphysical, okay? So this, literally speaking, when you optimize this, you have to be very careful. It's not easy to find the right solution, okay? It might be ill-behaved in some regions. There is always correct solution, but there are other solutions. Very hard to get the right solution always. So, but in this particular case, we're not so concerned about this. Why? Because we are using Luttinger-Ward functional for deriving things, okay? At the end of the day, we are going to always get this Luttinger-Ward functional from impurity problem. We're going to solve impurity problem where these problems don't occur, okay? We're going to circumvent the problem. Yeah, so the important point is that with this functional, it turns out that these terms here are very easy to write. This is very easy to calculate. They all depend on the Green's function, which is the basic object of our theory. The only problematic part here is this phi functional, okay? This phi functional here is something like exchange correlation functional in DFT, okay? And we will relate this very specifically, how they are related, okay? And this phi functional, however, in DFT, it's completely unknown, okay? In DFT, you really don't know what it is. You have to get it from a Gilliam model. But here you know, at least in perturbation theory, that this is sum of all connected two-particle irreducible Feynman diagrams, skeleton diagrams, okay? You just need to have a good way of calculating it. Well, if you want to do this on a lattice, that's hard. As I said, it's a problem because it's highly nonlinear functional, and you know, finding the correct solution out of many, many, many solutions that this thing has, it's really tough. I mean, we are trying to do this for some simple systems with the grammatic Monte Carlo now, and for some systems, you can actually calculate this in the perturbative regime, exactly, up to very, very high orders. But in most solids, you still cannot do that, okay? So then you have to approximate this. And the important point, we are going to approximate phi functional rather than the gamma functional. You should not make approximation on the free energy or total energy, or just fudge with kinetic term or potential term. You always should change the phi functional, okay? That's the important point, because then you will have stationarity, and you have a set of equations that where the total energy, self energy, and all of them are consistent, and you have conserving approximation, which means that it doesn't matter how you calculate, for example, total energy. It doesn't matter how you calculate the on-site occupation and so on. They all should be consistent. Okay, so so-called conservation laws are going to be obeyed. Okay, so now. Up to now, this was exact, but what do we do in DMFT? Well, what we do is we truncate in the phi functional, we truncate the variable, which Green's function, which is in general non-local, we truncate in the phi functional the variable so that the Green's only the local component of the Green's function enters the functional. Okay, that's the approximation. That's the only approximation, and we sum over I. And you see that this is very similar to DFT. What do we do in DFT? Well, in DFT, we truncate the variable to the local charge density, but local to a point in 3D space. And then we integrate over the entire space. Here we sum over all the sites, okay? And we truncate the variable to a site. That's the difference, okay? So otherwise, this is extremely similar, okay? Now, then we can write Feynman diagrams again, and this is phi exact, as I said before. It's sum of all vacuum-to-vacuum skeleton diagrams, okay? Of course, I just added here 3 dots, which means all the diagrams, arbitrarily complicated, arbitrarily high order. Now, within DMFT, what we do is we sum over all sites, and now all the vertices here in all the diagrams correspond to the same site, okay? And these propagators here are Fourier dress propagators, okay? Fourier dress propagators, that's the physical Green's function, and then everything truncated to the same site, so therefore only local interaction enters, isn't it? So that's the DMFT approximation for the solid, okay? And it's very similar to what you do in DFT, except that here you map to an ion rather than to a point in 3D space, okay? Now, of course, in practice, we never sum up these infinite set of Feynman diagrams, because that numerically is extremely hard, and it's also somewhat ill-posed, as I said. There are many solutions which are wrong. Okay, because it's highly non-linear. Now, what we do, however, is that's a very important contribution of Gabriel Kotler and Juan George, that they realize that if I solve a quantum impurity model, okay, then quantum impurity has exactly this sum of Feynman diagrams, exactly the same Feynman diagrams, because, well, that corresponds to the exact solution of the impurity. It has exactly this sum of the diagrams, okay? However, in order to equate this contribution from the impurity to what I need in DMFT, what do I need to achieve? Well, I need to achieve that all these propagators here exactly equate to each other, isn't it? So therefore, this interaction here, II, should be the same on the impurity than on the lattice, and all these propagators here, which are the Green's functions, on the lattice and on the impurity have to be the same, okay? So, in other words, if I make sure that this thing on the lattice, this GII on the lattice, is the same as G impurity, okay, then I'm really by calculating phi impurity, I'm calculating actually phi DMFT, for the site. Okay? So then I know if these two are equated, then I know that sigma impurity is the sigma self-energy on this site. Why? Because, well, sigma is always the functional derivative of phi with respect to g. Okay, that's one way of defining self-energy, the correct way of defining self-energy within the functional. Okay, so this is the simplest derivation of dynamical mean field theory equations, in my opinion. Okay, so just looking at at how the phi functionals correspond to each other, and then in some sense we understand now the impurity solver is just a trick to calculate this phi functional. That's it. Just like in DFT, you map each point in space to auxiliary Gilliam model, doesn't it? Now, the nice thing about Gilliam model is you don't need to solve it every time you calculate charge density. Why? Well, because it's one-dimensional function, and this one-dimensional function you can fit some QMC data, doesn't it, and store it once and forever, and you just calculate it on the fly. Here, this phi functional depends on the Green's function. Green's function has complicated frequency independence, and of course it's different for every has all the complicated on-site terms, U, crystal fields, and so on, and it's basically impossible to how can I say, store all the information. For any Green's function, you would need to calculate what a phi functional looks like. That's not possible, at least up to now. So therefore, what we need to do is we need to solve quantum impurity model, which gives you this phi functional. Okay, now the important point is this quantum impurity model is a trick to calculate the phi functional, and this quantum impurity problem is a very old problem, 50+ year old problem, and thermodynamics can be solved by numerical normalization group, and also dynamics can be solved, but unfortunately, if you have more than 3 orbitals, it's still very hard to solve, and it's very slow, and it's very hard to solve with numerical normalization group. Now, beta ansatz can be used to calculate thermodynamics, but only for the constant bath, constant hybridization, and for single band problem mostly. So therefore, unfortunately, this is not useful in DMFT, but it's very useful to understand the basic properties. For example, we know that if you go to exact 0 temperature, then you will either have Fermi liquid or you will have an insulator, a molten insulator. These are the two things that can really happen in single-site DMFT because we know the beta ansatz solution. Okay? But more than that, it's hard to say. Now, in DMFT, we typically need something like 5 orbitals or 7 orbitals for D or F problems, and therefore, we need a very robust generic impurity solver. And that actually was invented in 2007 by so-called continuous time quantum Monte Carlo. That was a quite important revolution, in my opinion, in this area, because it was realized that actually we can sum all Feynman diagrams, and that this can be done very efficiently with metropolis sampling, which is quite an interesting development. And this was, well, it turns out that you can do so-called weak coupling or you can do strong coupling expansion. Weak coupling expansion is used in many areas for the models mostly, but in real materials, the weak coupling is usually not used. Why? Well, because the bare Coulomb propulsions are very large, isn't it? And therefore, your Coulomb propulsion, typically where you start with, Coulomb propulsion is like 10 eV or something, and the bandwidth is much less, so therefore, you want to have something that can take into account very large Coulomb propulsions. So therefore, it's clear that strong coupling expansion is probably better, okay? And this strong coupling expansion actually was invented by Anderson and Uwali in the 1960s. They wrote down and solved within certain limits this so-called hybridization expansion. And then numerically, this was done by so-called continuous time quantum Monte Carlo. And basically, the idea is very simple. You have a generic Anderson impurity problem, isn't it, where this action has action for the atom and the hybridization. Okay, so that's the impurity problem, hybridization, where the electron can hop off or on this particular site. And then what you do is you expand with respect to this hybridization, just power expand, and this generates some Feynman diagrams. You can draw them if you want to, okay? But in reality, what we do is we just sample all those Feynman diagrams with metropolis sampling, and that's extremely efficient, okay? And it turns out there is a very weak sign problem. Many times it's completely absent. So here I'm drawing some Feynman diagrams. For example, the second order here, so-called OCA, the third order, the fourth order. These are all for single band, single impurity problem. But if you have more complicated problem, there are even more diagrams. They grow, of course, factorially. There are a huge number of diagrams. And this is an example of some iron moly system. And you see the perturbation order can be 500, 600, 700. Perturbation order is 700. That means that we have 700 factorial number of diagrams. Okay? So there is no way you can ever calculate them. Okay? Huge number of diagrams that you need. And basically, it turns out that the perturbation order goes as 1 over temperature. So when temperature goes to 0, it goes to infinity. Okay? But for any finite temperature, you can calculate that, isn't it? But the point is that the metropolis sampling is extremely efficient. Okay? It can randomly walk through this phase space of diagrams. It can get all these well, it can calculate self energy very well. Now the important point is that this allows correct treatment of all the multiplet physics, the physics that we just heard from Rebecca before. So it can take into account all on-site terms exactly. And of course, then in addition, there is a hopping hybridization, which gives you the hopping in and out of the impurity. But all the on-site terms are taken into account exactly.
What temperature can you go to reliably before the sign problem?
Well, in most of systems where you don't have very low symmetry structure, okay, where the hybridization is extremely off-diagonal, you can go to very, very low temperature. I mean, even in F systems, you can sometimes afford a few Kelvin. Or in D systems, you can afford any temperature, basically. You can see Fermi liquid. Okay, so this is not any more limitation, of course, in a big computer. Okay, so this CTQC is extremely efficient. The only problem, of course, here is that everything is on imaginary axis. Okay, so you do need analytic continuation. So, and in particular, this becomes a problem when you are dealing with screened interaction that Andre was discussing about, isn't it? So let's say that you're interested now in the two particle quantities in screened interaction, which has to do with irreducible vertices. Okay, so you would need to calculate irreducible vertex. Okay, you get it on the Matsubara axis. Okay, and then you need something on real axis. You need analytic continuation not for something that has one Matsubara frequency, but something that's 3 Matsubara frequencies, isn't it? So that's a challenge. Okay, that's a challenge for you, for new generation. How do we analytically continue two particle vertex function, okay, with 3 frequencies? If you can do that, you can solve lots of problems that have to do with screened interactions. Okay, yeah. So usually it's useful to look at the other approaches with the Luttinger-Ward functional, one important theory, of course, is density functional theory we discussed at the beginning. And it turns out, if you equate the phi functional, which in exact theory is sum of all skeleton diagrams, if we equate this functional with Hartree term plus exchange correlation term, we just do that, we are going to have exactly the same equation. We're going to produce exactly the same equation as in density functional theory. Exactly the same equations. Okay? So what does it tell you? It tells you the DFT equations can be looked at it in Luttinger-Ward functional as an approximation for the Green's function. So therefore, you should, in this Luttinger-Ward language, you are allowed to look at the bands. Okay? So in density functional theory, you should not look at the bands. But in this Luttinger-Ward picture, DFT bands are legitimate things. Okay? However, are obtained in the approximation where the exchange correlation is completely local to a point in 3D space, okay? The most local one, okay? So now, if you look at the dynamical mean field theory, then phi, we will, of course, always take into account the Hartree term exactly, and then we add all the actually, there should be sum over I. We take into account all the terms which are local to a site, okay? Sum over all I is missing here. Yeah, so it's in both cases, in DFT and then dynamical mean field theory, we have truncation in real space. One is truncation to a point, the other is truncation to a site or a few sites, okay? So there are, of course, alternative methods. In particular, Hartree-Fock is truncation in perturbation order, isn't it? So you can take into account the lowest order. Lowest order is the Hartree-Fock. RPA or GW sums up all the bubble diagrams. Why? Because these are the simplest diagrams to evaluate, isn't it? But it's very hard to evaluate those which are crossing. So you need some complicated Monte Carlo to take into account terms beyond that. Okay, so as I discussed before, DFT in language of this Luttinger-Ward functional shows you that that if you equate phi with Hartree plus exchange correlation, then you get exactly DFT equations. And exact DFT ground state energy, and the exact DFT gives you exact ground state energy and charge density. But in this approach, DFT is an approximation for the Green's function, which gives an approximate spectra, bands. The spectra can then be interpreted as a physical object within such an approximation. Now we make a conclusion. The fact that the bands are very reasonable within LDA and GGA is an indication that correlations are very local in real space. Okay? So the fact that actually LDA bands do make sense, okay, although in its theory it doesn't look reasonable that you should ever look at them, but they do look reasonable. So that means that correlations are local, are very local. So well, at least the local correlations are the one that you should take into account first. Okay? So weaker statement. The picture in which correlations are treated as local is very good. So convergence can be achieved faster when considering local correlations rather than long-range correlations. Now, there is one can write this even more precisely. Okay, so very illustrative example is again the uniform electron gas. Okay, and one can solve this now with so-called variation of the gammatic Monte Carlo, exactly. Okay, and one can see in which picture it's easier to solve this exactly. Okay, so either in the picture of long-range correlations or in the picture of short-range correlations. Okay, so how do we do that? Well, you can always map the system of electron gas or any solid-state problem into a system of bosons and fermions. Okay, instead of correlations, you write it, instead of on-site interaction, you write it in terms of interaction between bosons and fermions. And then for the bosons, you add some screening length here. So just write that the interaction is not q squared, but it's q squared plus lambda q. Okay, you can always do that. And then you have to subtract this lambda q as a counter term. Okay, you add something, you subtract something, isn't it? And then you do perturbation theory on it. And if you have a solver that can go to arbitrary high perturbation order, you can achieve the exact solution. Okay, so and that's what you can do with the gammatic Monte Carlo. And this is one calculation for so-called polarization at q is equal to 0, omega is equal to 0 for various orders. The first order, second order, third order, fourth order, fifth order. Okay? Now what I want you to take home is that when you choose this screening length lambda to be small, then the first order is reasonable, and the first order is actually RPA. Okay? First order is RPA or GW, and it's very reasonable. And it doesn't matter so much which lambda you take. It changes a little bit, but it doesn't matter so much. Okay? Maybe you shouldn't take it completely unscreened, but some lambda in reasonable range is okay. But then you take next order, and well, in this particular case, it's still okay. Okay? But in some case, it might be already blowing up. And then sooner or later, your perturbation theory will completely blow up. Okay? So what means that if you have a weakly screened model, then you will see that a higher perturbation order, you will not be able to get anything reasonable. Okay? It's very hard to converge something when your screening is weak. So, however, if you choose the screening to be large, okay, then you're reaching your solution slowly but steadily towards the exact solution. So the convergence is uniform. I mean, it turns out that, of course, for any lambda, eventually the system will break down. Okay, the perturbation theory will break down eventually, but you can get very, very, very close to exact solution. Okay, arbitrarily close if you can go to very high perturbation order. Okay, so that's an illustrative example that tells you how better the picture in which you take into account local correlations is than if you take into account if you start with the long-range correlations. Long-range correlations is extremely hard to converge. Okay, you should converge eventually, but you can't so easily converge it. Okay, so then the important point then is we should first take into account at least the local correlations exactly. Okay, so and in order to do this in solids, what we need is so-called projector. Why? Because we need to explain what is your local Green's function? The only way to do that is, well, you have to tell me what you mean with local, isn't it? So you have locality to a point in 3D space, that's very easy to define. Locality to an ion in 3D space, it's not so easy to define, isn't it? So you need to define it somehow. And of course, your choice will somewhat matter, okay? And that's the big discussion in this community. What is your best choice? Some one-year functions maybe, or some other orbitals. Which orbitals, isn't it? And of course, unfortunately, the results do depend a little bit on how you choose this orbital, okay? So therefore, well, different people have different philosophy, and I have one of them. And I will give you some arguments why I think mine is better, okay? But when you hear some other speaker, you might be convinced otherwise, okay? So bear this in mind. So yeah, so you need a projector. And generically, you can say, well, one way to write a projector is, of course, to write it as a product of some functions, and these functions are localized on a given site, Ri, isn't it? And in general, you can have many of these orbitals. Alpha, beta are some orbital indices. Now, if I allowed here Ri, Rj, I could write down the exact solution, isn't it? Okay, for any ij. But I'm truncating here to ii only. So it has to do with one site, okay? So therefore, what I can do is I can write the local Green's function as projection. I'm calculating the matrix elements here, as projection to this particular ii site, and then I embed this back into the lattice, okay? So this is projection, and this is embedding back into the real space, okay? But this you will recognize immediately as inserting this kind of projection in twice, isn't it?
What governs the choice of these points?
Well, that's an important question. That's a very important question. You have to have a good choice for that. So typically, what we do here is we take atomic orbitals, semi-atomic orbitals. So basically, solution of your atomic problem in a solid, isn't it? Dirac equation in a solid, okay? Up to the muffin-tin sphere will they start to touch. That's a very good choice. No. You can make it orthogonal. So what you do is you choose a very, very large window, okay? And then you orthogonalize within this large window. So we will see that basically the 5 functions are almost orthogonal, because when in infinite window, they should be exactly orthogonal, okay? But in finite window, they're not exactly orthogonal, but they're almost orthogonal. So, but yeah, of course, you need to orthonormalize. Of course, if you have one-year functions, then orthonormalization is actually problematic in the sense that some singular values might become 0 at some point, isn't it? So, but here, when you take large window, energy window, then the orthogonalization is never problematic. Okay, now it's time to write down the functional for the embedded dynamical mean field theory. Why embedded? Well, because we need to combine this with DFT. Why? Because we cannot solve everything with DMFT. It's just too expensive. So we take into account the Hartree exactly, okay? Then we add exchange correlation term for all the electrons, okay? Then we add all the local Feynman diagrams to those particular atoms which we know are correlated, like D or atoms or F, okay? And then we need to subtract what has been counted twice in both terms. And that's something I'm going to discuss tomorrow, okay? What is the exact double counting between the two? But this can be done, okay? So that's a well-defined process. So we have then a functional which we need to solve, okay? In principle, we could just write Hartree here, not exchange correlation, plus phi DMFT. But of course, that's not as good because there are many atoms such as oxygen or I don't know, many less correlated, or hydrogen, less correlated atoms, which you really don't want to solve quantum impurity problem for them, okay? Exchange correlation function is good enough. And then what you need to do is you need to optimize this functional with respect to your Green's function, with respect to your variable, which is basically just taking the functional derivative of this, and what you end up is so-called Dyson equation. So I wanted to do this a little bit more carefully with you, but I'm running out of time, isn't it? So what you do is you take the functional derivative of gamma with respect to g, and then the first term is very easy, okay? So trace log g, when you take functional derivative, you get g inverse. This g0 inverse minus g inverse times g gives you just g0 inverse, isn't it? That's very easy. Then you have to take derivative of Hartree plus exchange correlation function, which depends on density, and you have to use the chain rule. So we take the derivative with respect to rho, then the derivative of rho with respect to g. The chain rule, you look at the the definition of charge density and Green's function, you see that the difference between them is just a bunch of delta functions. So therefore, you get a bunch of delta functions here, isn't it? So then you take this term, and again, you take the derivative with respect to g, which is here. So you take the derivative with respect to this g in here. And that, again, can be done through the chain rule. You take the derivative with respect to the entire variable, times the derivative of this, what you have inside with respect to g, and you get these functions out, phi I, phi j, isn't it? These are now your embedders rather than the projectors. And then you do the same with double counting, and that's your equation, and it turns out this is the Dyson equation, isn't it? So therefore, you can rewrite it in terms of that how to calculate G inverse from G0 inverse. You add this DFT terms, and then you add your extra corrections due to quantum impurity model. Sigma impurity is what minus double counting. And yeah, so this impurity problem, of course, is calculated for each site, isn't it? With quantum impurity. Then the double counting, which I'm going to discuss next time, needs to be added. And this is basically it. So the important point is that once you define your projector through these orbitals phi that I defined before, once you define how to get from solid to an impurity problem, you also know how to go back. Because by this functional derivative, I just showed you that you know how to go from how to embed things back once you know how to project. Okay, so you just need these phi functionals. And now, one thing which I sometimes explain to the audience is that it's a good idea to have projector which is independent of the solution itself. Okay, why? Because only in this case you see that your functional is actually stationary, and that's useful. Okay, so why? Because when you take this derivative with respect to g, we said that this is derivative with respect to g local times derivative of g local with respect to g. Okay, and when we did this, we said, okay, only a bunch of delta functions come out. Okay, but this is true only when projector, this phi functional here, is independent of charge density. If this phi functional projector itself depends on the charge density, then you have some extra terms. Okay, and that, well, these are usually neglected. So therefore, it's a good idea to take projector which is independent of charge density. So this somehow eliminates Wannier functions. So Wannier functions from a small energy window will always give you these functions to depend on charge density, which means that your functional, well, at least this functional, will not be stationary for this case. So if you want stationarity, if you want to be able to calculate forces, okay, you rather make sure you don't use something that strongly depends on the charge density. Okay, so here is the summary then. What I tried to explain today is the following. If you have a way to calculate your Green's function of your solid, then you have to figure out which orbitals are correlated, and that's not that hard because you know what are partially occupied d or f orbitals. Then you project this to your local Green's function, calculate your local Green's function with the projector. Then you can solve a quantum impurity model, which is now available, where you can download it. Then you embed with the same set of functions phi to get your self-energy in a solid. And then you solve the Dyson equation for all electrons in a solid, and you get your Green's function. Okay? And that's what this algorithm is all about. So that's what we are iterating. Okay? And here there are a set of equations with which we do that, but that's pretty much the summary of this particular presentation.